So this problem, you'll find one like it in the Chamberlain-Bowles text in the 580s. I'm going to read it to you so you kind of get a feel for what it says. It says, at least the version in the 10th edition I found says cold water with a specific heat of 4.18 kilojoules per kilogram Kelvin, leading to a shower, enters a thin-walled double pipe counterflow heat exchanger. So this is a heat exchanger problem, and I just want to reread that. A thin-walled, double-pipe, counterflow heat exchanger, which really is just telling you adjective, adjective, adjective heat exchanger. It's thin-walled because you're going to have a very, very thin separation between the hot stream and the cold stream right here. It's counterflow, meaning that the outer stream is going to flow in one direction and the inner stream is going to flow in the other direction. Double pipe is a common type of heat exchanger. It's very easy to manufacture. You just take one pipe and you lay it inside of another pipe. And again, the counterflow mechanism means we're just going to flow the fluids in opposite directions. An advantage to this is you get kind of a more gentle cooling. You have the hottest of the hot water, the hottest of the hot stream is getting exposed to the warmest of the cool stream. The cool stream has been progressively warmed as it moves along, and the hot stream is getting progressively cooled. But each time, the hottest of the hot water is getting exposed to the warmest of the cool water. So if a huge temperature difference can cause thermal shock or degradation of the product, either product, a counterflow mechanism is actually a really good way of counteracting that. So it's a very effective way of doing it. But I just wanted to read that to you. Cold water, given specific heat, leading to a shower, enters a thin wall, double pipe, counterflow heat exchanger, which is just simply saying cold water enters a heat exchanger. It gives 15 degrees C at a rate of 0.6 kilograms per second, and it is heated to 45 degrees. The heating is occurring by hot water, which has a specific heat of 4.19 kilojoules per kilogram Kelvin, and it's entering at 100 degrees C at 3 kilograms per second. So all this information here is for the hot water stream going in. Determine the rate of heat. This one's asking for the rate of heat transfer. I'm not so worried about that. We can find it anyway. But what I really want to know is what is the exit temperature? What is the exit temperature of the hot water coming out? Which is really what I'm going to try to find. So example here. Find the temperature of the hot water coming out. So go ahead and copy this information down. If you need to pause and copy this information down, do that. I'm going to keep going to keep this video kind of short, but pause here if you need to. Okay, you got everything so far. So I'm going to go ahead and draw our system. Go ahead and I'm going to pause here and draw the system out. You go ahead and do the same. All right. And I should have told you before I said pause there that it's probably easier to draw the inside pipe first and then go back and draw the outside pipe around it. But that's okay, right? So now, this is what I would suggest is, you know how we normally label the inlet one and the outlet two? You could do that, but which one is which, right? And so it's up to you how you want to do that. I don't know that I'm going to be consistent with what they've done in the solutions here, but I'm just going to I'm going to use one, two, three, and four because I've got two inlets and two outlets. And it doesn't really matter which one you call which. This is the cold stream. I'm going to call the cold stream 1 and 2. I'm going to call the hot stream 3 and 4. You can call it whatever you like, but I think that's going to be easier than trying to write, notice what I've got here. I didn't know what to call these because I've not identified them yet. Now that I've identified these, I can say, all right, well, this is the cold stream. This is C sub P1, 2. Right? That's a CSP for the 1 and the 2, the inlet and the outlet of the cold stream. This is the cold in. This is T1. This is the cold out. That is T2. This is the cold inlet and the cold outlet. So it's going to be T1 and T2. This is the hot coming in. This is going to be T3. And this is the cold. I'm sorry. This is the C sub P for the hot water. So this is going to be, C sub P for the 3-4 string. Okay. And then one thing I didn't write here is they've also given me the M dots for the different streams here. So let's go back and get that real quick. M dot for the cold stream. So at the inlet of the cold, I've got zero point 0.6 kilograms per second coming in at what we're calling 1. And then coming in at zero point 0.3, it's got 3 kilograms per second. So we're going to write those down. So this is M dot at 1 is going to be 0.6 kilograms per second. And M dot coming in at 3 is going to be 3 kilograms per second. And they've also told us to assume liquid constant phase. Now that's really important. If you remember when we talked about specific heats, I said if the liquid stays a liquid or the solid stays a solid, then I can use specific heats. But if I don't know that it's staying constant phase, the specific heat changes once the phase changes. So if I'm dealing with any kind of ice crystals in there, or if I'm dealing with any kind of vapor in there, the specific heat's different. But if I've got liquid staying liquid or solid staying solid, I can use specific heat to find the change in enthalpy. Okay. So normally I would say, all right, what's a good tool for finding this unknown T hot out, which is just for us going to be T4. Um, and I'll normally wait, and somebody will normally just out of habit will say, well, what about the first law? Yes, let's look at the first law. Write your first law equation. I'm going to let you pause here and write a first law equation, see how you do with that. How do you do with the first law equation? Okay, how'd you do? In fact, I'm going to pause it and you can compare it to mine. All right, so this is what we have for first law. And the question becomes, okay, what do you call your system? Do you want to look at the whole thing as your system? If you're looking at the whole thing as your system, then I've just got energy of mass coming in minus energy of mass going out. Now, I could say, well, I've got one system is the cold stream. So I've got cold stream where I've got mass coming in, mass going out, and then I've got heat coming from the hot stream into the cold stream. So the cold stream would have Qn plus energy of mass in at 1 minus energy of mass out at 2. And then the hot stream, that means the hot stream would have mass coming in at 3 minus the heat that it's losing to the cold stream minus the energy of the mass going out at 4, and that's going to equal 0. So you could write two different equations with a common heat transfer between them. That's perfectly fine. We'll see that solution in a little bit. I wrote it this way. I said, you know what? It's just one system. There's no work being done in either case. And if I just look at the whole thing as one big system, well, I've got stuff coming in at 1, I've got stuff coming in at 3, and I've got stuff going out at 2 and stuff going out at 4, and that sum then goes to 0. Now, you might ask, I would hope somebody asks, hey, what about the speeds? Well, remember Steve's checklist for is the kinetic energy something, right? Well, do you have speeds? Well, no, speeds weren't given. Okay. Did it ask for the speeds? No, it just asked for a temperature. No speeds asked for. Okay. Is it a nozzle or a diffuser? No, neither of those things. The kinetic energy is important for those two devices. It might be important for other devices. Okay. Do you know the areas? Hey, had they said, if you had a massive area at the inlet here and a tiny little area at the outlet there, then there might be a significant kinetic change from the inlet to the outlet. Then I might want to include that a v squared over 2 and a v squared over 2 on either stream, but we don't know that. I think it's fair to assume it's probably the same area at the inlet and the outlet. So it's probably safe to assume that there's no significant kinetic change. And even if there is it going to be important compared to the enthalpy values? And I think that's really the assumption we're making here is that given the lack of ability to do anything useful with the kinetic energies, we're just going to assume that the enthalpy is the only driving factor here. And the good news is they gave us specific heat at 3 and 4, and they gave us specific heat at 1 and 2 for the hot and the cold stream. Now, so if we go ahead and collect, so if we collect the information again, I'm looking for T4. I'm looking for T4, and I know specific heat is going to allow me to relate the enthalpies to the temperatures given the specific heat. So I think I can convert basically these enthalpies to temperatures using specific heats. Let's look at the mass flow rates. I know m dot 1 and I know m dot 3, so these are known. What about m dot 2 and m dot 4? pause here if you don't have an answer for this. Pause about and think about, really think about how do I find m dot 2 and m dot 4 given this setup? What do you think? Go ahead and pause here and come back. All right, you got an answer? Right? This is kind of the best explanation I can give you is remember the the hot and the cold stream are separated. They don't mix. So I've got cold water coming in and I've got cold water coming out, and we're assuming this thing is steady flow, meaning that the mass coming in at the cold is equal to the mass going out for the hot. I'm sorry, mass coming in for the cold is equal to the mass going out for the cold. And the mass coming in for the hot is equal to the mass going out for the hot. Mass must be conserved. It's a steady flow system. There's no mixing between the two streams. So the mass into one stream has equal to the mass out of that same stream. So what do you got now? You got m dot 1 times h1 minus h2 plus m dot 3 times h3 minus h4, that sum's going to equal 0. So from here to here, and again, I know specific heats for each of these streams. So now m dot 1 C sub P12 times T1 minus T2 plus m dot 3 C sub P for the 3 for the hot stream times T3 minus T4, that sum's going to equal 0 because, again, we're assuming liquid constant phase. So a constant C sub P works for both of these. Again, realistically, this should be the integral of specific heat with respect to temperature. But since it's liquid staying at a constant phase, I can assume a constant specific heat. And therefore, that integral of C sub P dt just becomes C sub P delta T. We're good to go. I know all of this except for T4. T4 is my only unknown. Now it's just algebra and units. I'm going to work this out. Feel free to go ahead and work it out too. Let's compare answers. All right, how'd you do? Good amount of algebra to isolate that T4 out of here, right? You got to distribute m dot C sub P 3, 4 into both of these, solve for the T4 term, divide by the m dot C sub P 3, 4 term, and then you're good to go. All right, and then so now I've got T4 isolated. It's my only unknown. And then we start plugging numbers in, right? So m dot for the 1, 2 stream, C sub P 1, 2 stream. I left these in Celsius because a difference in Celsius is a difference in Kelvin. So you can just leave those in Celsius. Add to that m dot 3, C sub P 3, 4. You probably could have left this in Celsius because up here in the original derivation, this is a difference in temperatures. So since you have a difference in temperatures, Celsius is probably okay here. When in doubt, feel free to convert it to Kelvin. So I went ahead and converted it to Kelvin just to make sure. Divide by the m dot 3 and C sub P for the hot stream 3, 4. And then when you work that out, you get, if you're in kelvins here, you'll get about 367 Kelvin. You'll probably, if you run 100 here, you're probably going to get 94 because you're solving for the Celsius value. So here's where I would stop and I would ask my class, okay, does this make sense? Because notice I've got a big 30-degree temperature difference for the cold stream, right? Go back up here and look at our diagram. That cold stream is going 30-degree difference from the cold stream. And I'm saying I'm going from 100 to 94 on the hot stream. Why does that make sense? That I've got a 30-degree stream on the cold stream and a 6-degree swing on the hot stream. And I'll wait. I will wait until somebody gives me an answer, right? And eventually, it's right here. You see the comparison. I have more mass. The specific heat's essentially the same. Right? The specific heat's the same, not a huge difference, but the big difference is the mass. I have 5 times as much mass flow for the hot stream. So I should experience about 1/5 of the temperature change. So it's a 6-degree difference for the hot stream as compared to a 30-degree difference for the cold stream because I have 5 times the difference, right? 30 is a 1/6 of the difference here. So I'm sorry, a 1/5 of, right? So yeah, so you've got a 1/5 of the difference between the two streams because I've got 5 times as much mass flowing through the hot stream. That's the reason. If the specific heats are different, you still see that. You can see mathematically the balance. So if I've got, say, oil, like a solar powered hot water heater, where I've got some kind of an oily substance with a different specific heat, using that to heat up hot water in a hot water tank, a wonderful design. There are systems out there that do this. It's a very effective, cost-effective way of doing it. The control systems get to become a little expensive to replace, but that's another story. But you can do that, but that's just a situation where I've got different specific heats here and here. But if it's the same specific heat, if I've got um, 5 times more mass in the hot stream, I would expect 1/5 of the temperature in the cold stream. Now, let's go look at the solutions I've got in my slides because I think I do it a couple of ways here, right? Yeah, so here's another approach where we say, all right, well, let's treat the cold stream as its own system, and we can find the heat that's coming into the cold stream because I know specific heat and the temperature change for the cold stream. So I can set up a first law for the cold stream. That's Qn plus the energy of the mass in minus the energy of the mass out equals 0, or equals the energy of the mass out. Solve for Qn. So I can actually find how much heat's going into the cold stream based on its mass flow rate, its specific heat, and its temperature change. There's about 75 kilowatts of heat going into the cold stream, for example. And then that is the amount of heat that is being lost by the hot stream. So if I set up a first law for the hot stream, then the heat lost plus the energy of the mass in minus the energy of the mass out, that sum's going to be 0, and then just do your algebra. Then I can find the temperature out for the hot water. And you can see here, we can set up and get the same solution as what we just found, treating it as one single system. Either way is perfectly fine. If the problem asks for this heat transfer, this is the only way you're going to be able to do that. And I think in the original problem in the book, in the current version, it does ask for this heat transfer. Then you will have to set it up as 2 different streams and find the heat transfer between them. Just finding the one unknown temperature, and you can see mathematically you've got the same thing here. I'm saying that this is equal to the heat gained by the cold water stream. This is the heat lost by the hot water stream, and they're basically equal to each other. And I'm just solving around. I'm skipping this step of the algebra right here by setting up one equation there. Okay. All right. What does that leave us with? So I'm not gonna work through this example, but I am gonna show you, if you're just joining us from the internet, these solutions are available to my students, but I don't mind showing you the solutions to this problem here. Is this a realistic problem? No, probably not. But at any rate, you pause here, copy down the information. All right, you got it. And then so if you want this solution, here's how we work through it. Set up your givens. I've got places here where I can write down calculations and stuff. But basically, if you look at your conservation of mass, you've got 2 inlets and a single outlet. You use that to solve for your unknown outlet speed or your outlet mass flow rate. And then given that information, go ahead and pause here. I'm not going to dwell on this too long because, again, this is available to my students. I'm not going to work this full solution out, but I would encourage you, you can pause here, copy this down, or just come back to it. But I would encourage you to start here, pause it here, and see if you can get to the same solution I've already shown you. And I'm going to call that done for lecture 12. Thanks, guys.